Hello everybody, welcome to another ME296 lecture, and this time we're going to walk through a control system. We're going to set up our system, and then we're going to do some analysis. Not mathematical analysis, because we've already walked through how to do that, but instead an analysis of the considerations that we need to keep in mind when we're designing control systems. So first, let's go ahead and set up our system. We want to keep a sheet of some thin, light material floating at some height above a base. We are also going to need a sensor to detect the vertical distance of that sheet from our base, and this can be the ultrasonic sensor we've used before, or maybe some kind of laser sensor. Doesn't really matter in this particular case, but something that can detect the distance of an object. And then we need a fan that's going to provide the lift, because we're going to blow air at the bottom of the sheet and it's going to cause that sheet to float up or down based on how much power is being provided by the fan. So now let's determine the flow, our control flow. What happens in what order during a typical control cycle? The first thing that happens is that our sheet is going to be floating at some height. Then we're going to use our sensor to detect that height. Our sensor is going to send that information to a logical processor and determine if the height is what we want or if it's too high or too low. And then the processor is going to think about that for a second, and it's going to adjust the power sent to the fan based on the height, current height that was determined. If it's too high, send less power. If it's too low, send more power. The fan is going to adjust its speed based on the power provided to it by the processor. And then that sheet that's floating is going to adjust to a new height that is based on how much power is being provided by the fan. And then it's going to repeat. It's a cycle, not just one and done. So this keeps going until we turn our system off. And now let's think about a couple of things we need to determine before we even start building anything. What is fighting our system? We want to keep it at a certain height. What is trying to stop that? Well, the first thing that comes to mind is gravity. Gravity wants our sheet to be as low as possible, and it does so with a force determined by mgh, or gravitational potential. So the sheet is floating down based on its mass, the gravitational acceleration, and the height of the sheet from our source of gravity, the Earth, let's say. So in order to counteract that, we need to be able to provide at least that force of gravity plus some extra, because if it's too low, we need to be able to send it up. And if we can't provide more force going up, then gravity is going to stay at that height. If the sum of our forces is 0, we get no change. Then, how efficient are our components? What I mean by that is things like the fan motor efficiency. If we provide 15 joules of energy based on the current and the voltage to the fan, how much of that actually gets converted into lifting power to the sheet? How much energy is lost through atmospheric viscosity? And viscosity is a measure of how much a fluid wants to change the direction of force applied to it, more or less. So basically, if you push in a straight line on air, how much of it goes sideways instead of straight? Now, if it's a lot of stuff that wants to go sideways instead of up, then we lose a lot of energy from the air particles going sideways instead of straight up like we want them to. And another thing we need to consider is the granularity of our response. And what I mean by that is, how many settings does our fan have? If it's just on or off, then maybe we can get it to kind of stay at some kind of height based on pulsing the on-off thing, but it's not going to be very steady. But if we have 150 different speed variations on our fan, we have a lot more granularity. We have a lot more fine control. And there's a similar situation in the sensor. If our sensor can only detect close or far with nothing in between, it's going to be a lot harder to determine an appropriate response. But if our sensor has a million different distances it can effectively measure, we're going to be able to determine the distance a lot more effectively. The logical processor is going to have a lot more to work with. And then another thing we need to consider is the inertia of our system. And what I mean by that is how hard is it to change the behavior? If the sheet is really heavy and it starts settling down, it's going to take a lot more force to get it to stop going down and go back up. It's a lot harder to change what's already happening. But if our system has a very light sheet in it, it's very easy to change the inertia of our system, to change it going from down to up. So with that in mind, let's start diagramming our system, because now we know what we want to do and we know a couple of the basic things we need to keep in mind of just our system in general, of things in the world. So let's look at it through a diagram. What is our input? Our input is the sheet height. What is the output? The output of our system is actually the fan power. We don't directly control the sheet. What we do directly control is the fan, which controls how high the sheet goes as a response to that. But it's not like we have an armature or something we directly control that keeps it at a certain height. And then we need to consider what happens in the middle, the interpretation of the input and then a calculation of the output. So when we start diagramming, we look at this. We have our first input, which is our set point given by d of s, because we're in the Laplace domain, because we're doing a control system diagram. And right now we only have our set point height, and then we have h of s, our true height, or our actual measured height. That measured height is going to go into our controller, which has a transfer function all its own. And then that controller is going to determine the value of output it needs from the input of height. Then it's going to send that output to the fan, and that output is going to control how much power gets sent out. And then you have X, our fan output. And that fan output should then control the height. And that height gets measured by the sensor, M, where N is the sensor reading, and then it's going to connect back to the beginning through a summing point. Now it's negative because we're measuring the difference between our set point d of s and our actual measured height n of s. And then we're sending the error h to our control system. Our control system doesn't really need to know how high it is. If it's 50 centimeters from the base, that's not super important. What it needs to know is that it's 3 centimeters away from where we need it to be, because that's what's going to determine the adjustment of our system. So let's talk a little bit about measurement. Let's say our sensor can only detect discrete integer values, and we're going from an analog system to a discrete system now. And what that means, basically analog is a continuum. You can have as many fractional values as you want. And then a discrete system, you're set to a limited value, a limited set of values. And our sensor only can detect a limited set of values, so we're going from analog to discrete. And this is going to bring in a set of limitations on what our sensor can do for us. So let's give an example. We have an object that's exactly 15 distance units from our sensor, and that's great because 15 is one of those discrete measurement values that our sensor can read. So we're going to get an accurately reported distance. But what if we have another object that's 9.5 distance units from the sensor? This is bad. Our sensor cannot measure things that are only a half distance unit away from it. It needs to be a complete integer. So we're going to get a reported distance of just 9 distance units, even though it's 9.5. So what does that look like when we're seeing something moving? Let's say we have a plot where we have an object starting at 0 and moving away over time, and the true distance is given by that green line. Well, the reported distance, the distance that the sensor can detect, is given by that blue line. So we can see from the plot that we're wrong almost all of the time. And a question we need to ask ourselves is, does this matter to us for the system that we're looking at? Are we so wrong that the information is unusable, that we can't do anything with it? Or are we correct enough that we can still use this information? And for the sake of the system we're designing, let's just go ahead and say, yeah, we're right enough. Now let's talk about the controller a little bit. Our controller is going to determine how much power to send to the fan. And we can model this using a controller response curve. The input to our controller is the error. So we have some kind of input, our x value, if you want to look at it like a function. So we'll plot it as an x-axis. Input is error, which is the distance between the height we want it to be and the height that it is. What we want it to be minus what it is our error. The output is going to be fan power, or how much power we send to the fan. We'll put that as the y-axis because that is dependent on our input, so it's the dependent variable goes on the y-axis. And now we need to ask ourselves, how much output do we need for a given input? Let's assume for the time being that a linear response is just fine, where for every value of input we go through, we have just a straight multiple of that input that gives us an output to our fan power. And we need to ask ourselves if that is okay. Remember, we're dealing with a couple of limitations such as viscosity in the atmosphere. Maybe when we're further away, we need more power than we would for a given change in distance than we would if we were near. Maybe we need instead an exponential kind of response curve because we need to have a lot of output change for something that's very far away from our set desired point than we do for something in the middle. And that might make sense because remember that power falls as the radius squared, 1 over the radius squared. So the further away we get, we're losing more and more power to distance and radiating from the sides, the viscosity of the atmosphere. So maybe we need that. But for this system, let's assume that our distances are small enough that we can model everything as a straight line, and then just talk about the linear stuff. We need to talk about the granularity of our control system based on the granularity of our input. So that's going to look like this. Our input can only give us measurements on those orange dots, which means that our output curve can only look at information based on those orange dots. Our output is only based on that, which is separating everything. It's no longer a curve, it's a set of responses that we can model as a curve. And we can take this even further. What if our output of our controller is limited to only a couple of different values? And that's going to be affected by the fan too. So if our controller knows that the fan can only be on or off with no in between, then you're just going to have a simple bang bang system. It's on or it's off. So the controller response curve is just going to be a step function. But if you can get different kinds of values, maybe you have some kind of frequency modulation, or you can adjust the voltage you send to the fan, then you can get more and more fine control, and you're going to start more approaching a straight line. So that's the kind of thing you need to keep in mind for talking about a controller and thinking about what kind of controller can we use. For example, the Arduino that we use has potential inputs of 1024. You can take 1024 discrete input measurements. Is that going to be enough for our system? Maybe, probably. It will be in this class. We certainly wouldn't want to design anything that we're incapable of constructing, at least in our labs. But later on, when you're designing things on your own, maybe for your senior project, you're going to need to think about these things without knowing the answer already. If you're doing something that requires a great deal of precision, you may need to find a different way to control or a way to smooth or interpret the readings so that you can more accurately gauge your output needs. So let's recap a little bit. We need to know the flow of our system when we're designing it. We need to know what we want and the steps we need to take to accomplish them. We need to know the limitations of our system. We know that we're going to be wrong most of the time, but how wrong are we, and do we need to do anything about it to make our goals happen? And only then can we design our system interactions. What kind of response curve are we looking for our controller? If we're looking for an inverse, so if we have a high input and we're looking for a low output, we need to design that system and program that into our logic controller. We need to know how much power we need to provide to our mechanism that's actually doing the controlling, our actuator. If we need to provide more power, maybe we need a second external source of power. If we need to provide less power because we're overdoing it, maybe we need to implement some kind of voltage divider to suck some of that energy away. So that's basically what I wanted to cover for this lecture, was just kind of a reinforcement of the kinds of questions that we need to be asking when we're designing a system and the kinds of things to think about when we're analyzing a system, because everything I just covered applies to every system for the most part in broad strokes. For example, the temperature controller lab that we did, our granularity of input was 1024. We could read 1024 different values of temperature. And was that enough to control our system, keep it within the range? It was in this case, but what if we needed a very precise range? What if we're doing a very delicate chemical interaction and we need to keep that reaction chamber at exactly the correct temperature? Would 1024 values be enough? Maybe we would need to figure out a way to increase that value, make it more sensitive. Maybe we need to have a better control system than just on or off for our fan or for the heating element that we used in the lab for the temperature controller. These are the kinds of things that we need to consider when building and designing systems. But that's all for now. I'll see you later.